Okay, so let's start. Is there any question? Any of you?
No, sir.
Okay, then let's start. Okay, good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL PMRF TA for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. Uh, he is a faculty in IIT Kharagpur. Okay, this is a 12-week course, and I hope you people have watched the first week lessons. Okay, so this is our first week problem solving session, and in this session we will discuss about the mainly the basic concepts which we have already discussed in the first week lecture, and then we will solve some questions based on those topics. Okay, so before starting, uh, let me discuss the outlines of the course. Okay. So these are the outlines. I'm just telling a brief intro about the 12-week course. Okay. So like in week one, we will discuss about sets, classes, collections, ring, field, sigma ring, sigma field, and monotone classes. And then we will discuss the random experiment, events, definition of probability, and some properties of probability function. Then we will discuss conditional probability in week two, then independence of the events, problems related to those probability, and random variables, probability distributions, etc. Week three, we will discuss about moment and moment generating function, characteristics of distribution, and some common spatial discrete distribution functions like binomial, Poisson, Bernoulli, hypergeometric, negative binomial, etc. Then in the subsequent week, we will discuss about Poisson process and some spatial continuous kinds of distribution like exponential distribution, normal distribution, beta, gamma, etc. Then in week five, we will discuss normal distribution and the properties of the normal distribution. Then in week six, we will discuss about functions of random variables. Okay. Joint distribution functions, independence of random variables, their product moments, the linearity property, and the correlation of random variables between the random variables. Further, we will discuss about bivariate normal distribution, which is a special kind of multivariate normal distribution. Then additive property of the bivariate normal distribution, transformation of random variables, and then at last order statistics. In week 8, we will discuss basic concepts related to chi-square, T, and F distribution, and then descriptive statistics. These T, chi, and F distributions are collectively called small sampling distribution. And in descriptive statistics, we will discuss about like the measure of central tendency, measure of dispersion, skewness, and kurtosis coefficients. Then up to this week 8, we have covered the probability part of our syllabus, okay, of our course. And then in week 9, we will discuss about statistics. And this will be started by defining descriptive statistics again, then introduction to estimation, unbiased, consistency, sufficiency, completeness. These are the properties of an estimator. Then we will discuss about some estimation techniques like least square method, method of moment estimator, problems related to those estimators. Week 10, we will discuss about maximum likelihood estimation with some examples, uniformly minimum variance unbiased estimator, their properties, sufficiency, completeness, Rao-Blackwell theorem, and At last, we will discuss about interval estimation in week 10, which is also part of statistical inference. Then we will discuss in week 11 different kind testing of hypothesis, basic definitions, basic terminologies. Then two types of error are there in hypothesis testing. Then Neyman-Pearson lemma and applications of those NP lemma. And at last, we will use our hypothesis testing concept to test for normal mean, for normal variance, for for variance, as well as proportion as well, pair t-test, and some examples related to those testing mechanism. These are the overall topic that we will discuss in this course one by one. Okay, so if anyone want to say anything or want to share anything, then he or she may directly ask me. Okay, or any point, if you are not able to understand the question or the solution, how we will proceed in those questions, then you may directly ask me. Okay. Okay, then.
Sir,
So let.
I have.
Yeah. Yes. Yes.
Hi, sir. I have one question. So I just enrolled into this particular course this week, and I couldn't finish my week one's concepts yet. So I believe I'll
Okay.
be able to follow up today. Can you?
Yeah. Yeah. Actually, if you are not like watching all those lectures, there are 8 lectures actually in week
Yeah, yeah.
one. So there is no much problem. I will discuss some of the lectures concept as well. Okay. In the
Oh,
first 20 to 30 minutes, I will try to just recall those concepts, those formulas or properties, and then we will solve, sorry, then we will solve some basic questions. Okay. And
okay.
during the question, if you face any problem, then you will ask at that time only.
Okay,
Okay.
sure, sir. And this class will be held every week.
Yes, every week on Tuesday, 6 to 8 p.m.
Okay, okay. Thank you, sir. Please continue.
Okay, then, we will discuss about algebra of sets. Okay, the first week is like algebra of sets, and then we will go to probability and definitions of probability. So, as we know that, we have sample space. So, collection of all those elements. Okay, all those possible collection of all possible outcomes. Okay, that contain in a set that is known as sample space. Okay, there is a finite or empty set as well, which is denoted by the phi. These are the notations which we will use throughout our lecture. These are the empty set. The notation for empty set is phi actually. Okay, there is a definition of class. Suppose when I am telling about a class, then that means it is nothing but a set of sets. The set of sets is a class. If you people may remember, a well-defined collection of object is known as set. Okay, then there are subset of a set, and the collection of all those subset is a class as well, which is particularly known as power set of that subset. Okay, these are already discussed in 12th standard actually. Okay, then if we are telling about collection, then in that case, these are set of classes. If uh, if like we will discuss about class, then set of sets, power set is one of the example of class, and collection of set of classes. Okay, then let's start by defining limit of a sequence of sets. These are some of the topic that is already covered. I'm just naming them or taking some snapshots. Okay, so like limit of a sequence of a set. Okay, so let we have a sequence En. Okay, be a sequence of subset of a sample space or universal set omega, then we may define the E upper star, which is limit supremum. Limit supremum of this sequence En. Okay. And the meaning of this is what? Like all those elements belongs to the sample space such that X belongs to the sequence En for all infinitely many values of 1. Okay. And in a similar manner, if we define the limit infimum, which is E lower star, that is defined as X belongs to omega, X belongs to omega, such that X belongs to En for all but finitely many values of N. Okay, so these are the definition of limit of a sequence. Okay, so from here we will define monotonic sequence. Okay, so like monotonic sequences. So there are, we will define two monotonic sequence here. The first one is monotonic increasing sequence. So like a sequence En is said to be monotonic increasing sequence if we have En is a subset of E of n plus 1 or n equals 1, 2, and so on. Okay, so that means every subsequent member of a sequence is containing the previous sequence. Okay, so En subset of En plus 1. These are mo similarly monotonic decreasing sequence is defined as like a sequence En is said to be monotonic decreasing if En is a En plus 1 is a subset of En actually, or n equal to 1 to so on. Okay, so like we can have some examples even. Like if we take the sequence 0, 1 by n. So can anyone tell me for n equal to obviously 1, 2, and so on? So can anyone tell me, is it monotonic increasing or monotonic decreasing? Anyone?
Sir, increasing.
How can anyone tell me how? Like here we can see now at n equal to 1, it's it E1 is nothing but the interval of 0, 1, open interval 0, 1. E2 is 0 to 1 by 2. So here E1, E2. So again, it is like increasing or decreasing. I think it is monotonic decreasing. Na? Okay.
Decreasing.
Yes, decreasing because the E2 contains in E1. Yes. Or we can also one more example. Like if we take En equal to minus n to n. In that case, En is anyone? Here we can see that this part is our E1 and this part is E2. So clearly it is visible like E1 is a subset of E2. And this is the definition for monotonically increasing sequence. Okay. So these are the examples of monotonic increasing and monotonic decreasing sequence. Okay. There are various things that is discussed. Actually, there are 4-hour lecture for in week 1. So I'm not going to discuss all those topics, just some of the topics we will catch. Like there is one more topic, symmetric difference. Okay, so symmetric difference is defined as like A and B are two sets. Then asymmetric difference B is defined as like A difference B union B difference A. Okay, so this can also be like visualized with the help of Venn diagram. You want to see, suppose it is our A, it is our B. So A difference B is nothing but this. Okay, and B difference A is this. So this can also be like rewritten as A union B. You can visualize with the help of this Venn diagram. This can be written as A union B difference A intersection B, because this part is actually intersection part. Okay. So these are the definition for symmetric difference. All the set operations can be applied here in probability theory as well. Okay. There are various more properties, like if I can write E difference B is E difference E intersection F, which is also like E union F difference F. These all can be verified or visualized with the help of Venn diagram, or you can prove with some other method as well, like E intersection F difference G is nothing but E difference F different, sorry, E intersection F difference E intersection G. This is distributive actually. If you can see, this second one is the distributive law in intersection and difference. Similarly, there are many more properties. Actually, there are 16 to 17 properties that has been like taught in the lecture. Like here, symmetric difference phi. The any set E with operated symmetric difference with phi set, then we will get actually the same set E. If we will operate this symmetric difference with the whole sample space, then we will get E complement actually. Or like on the same set, we will get nothing but phi. So there are various type of properties already given. Okay. And symmetric difference operator is like commutative in nature, like commutative in nature. So we can write E symmetric difference F is equal to F symmetric difference E. Also associative property like E symmetric difference F symmetric difference G is equal to E symmetric difference F symmetric difference G. This is like associative property. This is commutative property. And yes, the distributive property as well, like E intersection F symmetric difference G. So the intersection is distributed to F as well as G. So E intersection F symmetric difference E intersection G. So this is our distributive property. So symmetric difference operator follow commutative, associative, and distributive property as well. And there are many more properties that you people can see in lecture. Okay, so we will now discuss about rings, fields, sigma ring, sigma field. Okay, and then we will define probability theory, the definition of probability. Okay, so like ring. So a non-empty class, suppose a non-empty class, suppose cursive R, of subset of omega, subset of sample space omega, is said to be a ring if the following conditions is satisfied. So there are mainly two conditions. The first one is if A and B belongs to the ring, is defined A union B must also belongs to the same ring. This is the first property, first condition actually. And second one is if A and B belongs to the ring, then the difference A difference B must also belongs to the same ring. If these two property holds, then that subset of the sample space is called ring. Okay, there are various property like phi is a ring, like empty set is actually a ring because phi suppose we take this equal to phi, then obviously phi belongs to every set. Okay, so phi belongs to R, then the first is phi union phi, which is equal to phi, that is empty set. Also, the difference between this is also empty set, which is also belongs to. So that means the smallest ring is empty set. Okay, then power set is also there, which is the set of all subset of a sample space. Set of all subsets of a subset of the sample space omega. These are the power set, and 100% we can say that power set is the largest ring for the corresponding sample space. Okay, these are some of the properties actually. Okay, then we will, in a similar manner, define field. Okay, field, it is also like termed as algebra. So like in ring, we have these two property. If AB belongs to the ring, then A union. Hello.
Yes, sir.
If someone has asked me, will the recording of this live lecture be uploaded on the course page? Yes. The answer is yes. And will we get these notes or recording of this lecture on the course page? Yes, yes. Divya and Athar, the recording as well as this script, both will be provided to you by the NPTEL team. Okay. And if you have any doubt or want to ask anything, then directly you can ask because I'm not like looking in the chat box. Okay, so yes, now as we define ring, like if A and B belongs to the ring, then A union B and A difference B must also be there in the ring. So if these two condition holds, then that subset of that of the sample space is called ring. In a similar manner, like there is one more condition, we can say algebra can be defined a non-empty, suppose a non-empty class, let's call A, cursive A. Okay, it is a subset of omega, which is a sample space. Then, if these two conditions are satisfied, like if A and B belongs to the cursive A, then A union B must also belongs to cursive A, which is same as we define in the ring. Now, the second one is a little bit different. That is, A is a set which is belongs to the cursive A. This implies the complement of A must also be there in the, need to write here A. The complement of the set should also be there in the subset. Then that subset of the sample space is known as field. Okay, so there is one slight difference there. It is a difference. A difference B must be in the ring. And here, the complement of that set, that is A complement, should also be there in the subset. So then if these two conditions satisfied, we say that the cursive A is nothing but a field or algebra. Okay. So now there is sigma ring. There are various property actually.
Can you explain the second?
Algebra.
Sir, please can you explain the second property of field again?
Okay, okay. So see here, like there is slight difference. Like if A and B are element of the subset like cursive R, okay, then A union B should also be there if this first condition holds, and this first condition is same for ring as well as for field. Okay, you can see. Now the second condition is if A and B belongs to the subset, then A difference B should also be there in the subset. If these two conditions satisfy, then it is a ring. It is a ring. But if instead of the difference part, if the complement of that element is also there, that set is also there, then we say that this cursive A is field. That is, field is the upgradation of the ring, we can say. Okay. If you want some, yes, there are many examples actually. Sir has already taught all those examples. I'm not like going to discuss here because we need to solve some 10 questions here as well. Okay. So I'm just reminding how the field, what is field and what is ring is defined. Then what is semi-ring? Semi-ring also, not sigma ring first. Semi-ring is also there, but let me first define sigma ring. So like sigma ring, again, a non-empty class, suppose is cursive S, okay, of subset of omega, which is a subset of the sample space omega. It is said to be a sigma ring if, now the condition is slightly changed. E and F belongs to the cursive S. This implies the difference part is there. Okay. And the second part is slight difference, like for any sequence En belongs to the cursive S. This implies the union from 1 to infinity of En should also be there in the cursive S. Okay. This is the second part actually, if you can remind. This is the ring second condition. The ring second condition is E minus if is also be there. But if for any sequence En belongs to S, then the infinite union of those En should also be there in the same subset, then that subset is called sigma ring. Okay, this is the slide. So we can like there are okay, like there are many remarks actually we can conclude or observe from there. Like every sigma ring is a ring. That is, when we update some more property in ring, then it is may convert into sigma ring. Okay, there are or more properties like if a ring closed under the formation of countable unions, then it is also a sigma ring. Okay, like here, like union n from 1 to n, En should also belongs to this. Okay, so this is also a sigma ring, which is a the specific case for the second condition of the sigma ring. Also, if En belongs to S, then okay, there is a property actually. It is closed under the formation of countable unions. This is the property already defined and proved in the lecture. Okay, so sigma ring is closed under the formation of countable unions. Also, sigma ring is closed under the formation of limit operations on the sequence of sets. Okay, so these are already defined. So just I'm leaving those topics. Now there is also sigma field or sigma algebra. Okay, so similarly, as we define field, maybe we can manipulate or modify some terms, some conditions. Then we will define sigma field. A non-empty set of class, uh, a non-empty class of subset of omega is said to be a sigma field if the first condition, suppose it is we define cursive f. So if E belongs to cursive f, then E complement also belongs to cursive f. This is already defined actually. The second condition of the field is this. Okay, here we have defined here second condition. Okay, so now one more condition, and the condition is like if En is a sequence belongs to the belongs to the field, then the infinite union of En must also be there. Okay, so if you can see the similar as the condition for sigma ring, so the sigma field and sigma ring has the same second condition, but for the first condition, it is taken from the field definition. Okay, so these are the definition of sigma ring, sigma field. Okay, there are many properties of sigma field as well. Like sigma field is nothing but a sigma ring. So every sigma field is a sigma ring. Uh, so we can say that every sigma field is a ring as well. So we may say that uh, every sigma field is a field even. Okay, so every sigma field is a sigma ring. Okay, and every sigma field is ring even, and every sigma field is field. Okay, so that means sigma field is one of the specific part of ring or field. Okay, there are various properties or remarks of the sigma field as well, like a sigma ring closed under the formation of complements of a sigma field. As also, a sigma ring containing omega is a sigma field, because if we have the sample space in the subset, then this the second property, or here the first property actually, this can also be satisfied if this subset contains omega, then this condition also satisfies. Okay, so hello.
Yes, sir.
Yes, sir.
Okay. I think there is some network problem. Is my screen visible?
Yes, sir.
And am I audible as well?
Yes, sir.
Okay. Okay, then these are the definition of like sigma field, sigma and sigma ring and field and ring. Okay. There is also a semi ring. Okay. So if E belongs to that subset of a set, suppose cursive P, then that either intersection should also be there. This is the first condition. And similarly, if there are two conditions, then okay, that is actually quite long. So I'm not going to like write all those. These are already there. So we will start the definition of like probability. Okay. So our topic is probability and statistics. So we will start probability theory now from here. So let me first start with experiment. Okay, the probability theory is like mainly developed in 15 mid 15th centuries actually. So mid 15 or we can say 16 to 17th century. Mid 15 that means 16 to 17th centuries in gambling house. Okay, this probability theory is start in 16 to 17th century in gambling houses. Okay, by their owner and the initial development credit goes to like Pascal and Permet. Okay, they are the two mathematicians who coined the concept of probability. And let's like define some basic terms that we will use in probability. Like first is experiment. Okay, so like an experiment is what? Like when an experiment is observing something happening, or we can say that we conduct something under certain condition and we have some outcomes, then those are called experiments. Okay, so there are mainly two kinds of experiments. The one is deterministic and the second one is random. So deterministic is like suppose we add hydrogen plus oxygen, then we know that what we will get. We will get nothing but water. Okay, so already we perform the experiment and we know what we will get as an outcome. And in random experiment, we do not have a specific knowledge that what we will get as an outcome. Suppose like when we toss a coin, we have a we have a set of outcomes. Okay, but we do not know that which outcome will we will get in that particular trial. So that is random in nature. So there are two kinds of experiments, deterministic and random experiment. And in this probability theory, we will discuss about only random experiment. Okay, there are some more terms like sample space that is already defined. Sample space that is defined as the possible outcomes, the set of possible outcomes. The set of possible outcomes is called sample space. And then there are events. Events is like defined as the subset of this sample space. Okay, like suppose we perform a random experiment, tossing a coin, tossing two coins. for example, when we toss two coins, then we will get head and head, head and tail and head and tail on both sides. So these are the we perform the random experiment is tossing a coin. Okay, and the sample space is like this, which we will denote it as omega, and event may be getting two head. Suppose like even getting two head. So that means we have this as an event outcome. And this favorable outcome is a subset of the sample space omega. So event is defined as a subset of the sample space omega. Okay, we will define all those things actually. Like also, suppose we roll a die, then we have these information, these possible outcomes will be there. Okay, and suppose we define the event even like prime numbers, set of prime numbers, that is 2, 3, 5. If we say E2 odd numbers, 1, 3, 5, and these all 2, 3, 5 subset of omega, 1, 3, 5 subset of omega, it's omega 1. Okay, so event is defined as the subset of the sample space omega. Okay, so there are also, suppose I define E3 multiple of 7. Okay, now there is a problem because there is 5. There is 5 because there is no element 7 in omega 1. So when we like these kind of when we will discuss about these kind of events, then it is termed as impossible events. So those events who have zero probability, which we will discuss in later actually, or which have zero cardinality, the set having zero cardinality, those are called impossible events. Similarly, sure events is also there. When our event, suppose E4, our event E4 is equal to the sample space, is equivalent to the sample space, then obviously the probability of those events must equals 1. So this is sure event. So these are some terminologies. Also there are okay, wait. Okay, so there is some more events like exhaustive events. Exhaustive events like there are, suppose we have a sample space omega. Okay, so we can partition this sample space into many smaller sets. Okay, so suppose A1, A2, AN. Suppose we have partitioned this omega sample space into n smaller sets. Then if union of this AI equal to the omega, then we say that AIs are exhaustive events. If the collection, sorry, if the union of the subsets comes to be the sample space, then those subsets are termed as exhaustive events. Okay. And from there, we will define some more properties of the probability function later on. Okay, so the exhaustive events is there. Then there is equally likely events. So suppose we toss a coin. Okay. So in tossing a coin, the probability of getting head as well as probability of getting tail is both equal 1 by 2. So there, the event of happening head as well as happening tail are equal. So those events who have equal chance of equal probability of occurrence is called equally likely event. Okay. Suppose A and B are two events, then probability of A equal to probability of B. Then we can say A and B are equally likely. Okay, equally likely event. Also, these terms are going to be used in the definition of probability. That's why I'm just telling exhaustive events, equally likely events. There is one more like mutually exclusive. Mutually exclusive events. So suppose again we have two events A and B, which is set of omega. Okay, then if A intersects at B is phi, then we say that A and B are mutually exclusive events, or it is also termed as disjoint events. Okay, so these are some of the terms that is going to be used in the definition. So let's start the definition of the probability theory. The first one is classical definition. There is three definition actually. There are three definition of probability. Okay, the first one is classical, which is also known as mathematical definition. So in this definition, this one is mainly uh, okay. This one is given by Laplace in 1812. Okay, suppose a random experiment has n outcomes, and these n outcomes are like mutually exclusive, exhaustive, and equally likely. Suppose n outcomes are mutually exclusive, exhaustive, and equally likely events, then uh, then also let m are some of the favorable outcomes out of those n outcomes. Out of those n outcomes, m are the favorable outcomes, favorable number of outcomes. Then, according to the classical definition of probability, the probability of the event, suppose event name is A, is defined as the ratio of m by n. This is the classical definition of probability. So that is favorable outcome is divided by the total number of outcomes when those outcomes are mutually exclusive, exhaustive, and equally likely, then those are called mathematical or classical probability. Okay. Similarly, there are some drawbacks of this classical definition, like n needs to be finite here. This needs to be finite, the denominator. Also, the definition is circular in nature. Actually, here, when uh, here equally likely events, when I'm telling about the equally likely events, then I'm already discussing about the probability, like probability of A equal to probability of B. And up to this point, we do not know about the probability. And also in classical definition, we will define the probability with the help of the equally likely events, which is defined on the basis of probability. So it is circular in nature. Okay, so these are the drawbacks of the classical or mathematical definition of probability. So to like resolve this, we have the second definition of probability, which is statistical or empirical. In this definition, we perform the random experiment. Okay, suppose a random experiment is conducted a large number of times, independently under some constant or identical condition. Suppose when we toss a coin, then we will tossing the same coin on the same surroundings. Okay. Or when we roll a die, the die must be the similar in nature. Like there is no rolling circular die will be there. Okay. So under identical condition, when we perform a random experiment a multiple number of times, okay. Also let an denote the number of times the event A occurs. Number of times event A occurs. Okay, occurs. Then in classical definition, the probability is defined as the limiting case. Then the probability of the event A is limit n tends to infinity. It's an upon n. Okay. So this is the classical definition. Here n may take infinite value. Okay. Also, there is some more drawbacks in this statistical or empirical definition of probability. That is, here we perform the random experiment, but every time it may not possible to get the outcome, the result from the experiment. So there are some cases. Also, like if we have some favorable condition like under root times of those the total outcomes, then in that scenario, if we perform the limit on this, we perform limit, it will comes out to be zero. But this implies there is zero favorable outcomes, but there is under root n favorable outcomes in our favor. Okay, so these are also one of the drawback of the statistical or empirical definition of probability. So in a similar manner, suppose we have a favorable condition like n minus under root of n, and the total condition, total outcomes is n. Then it comes to be 1 when we apply the limit. So again, it neglect the favorable outcome as compared to as compare we will like acknowledge in the classical definition the favorable outcome. Okay, so these are two drawbacks of statistical or empirical definition of probability as well. Now the main definition. This is the last topic, and then we will solve some numericals. Okay. So there is one more definition, that is axiomatic definition of probability. And the axiomatic definition of probability is not defining the probability, it imposes some condition. Okay. There are three axioms actually. Axiomatic definition. Okay. So this one was given in 1933 by a Russian mathematician Kolmogorov. Kolmogorov. Okay, so he defined the axiomatic definition, and for that we need to understand the measurable space first. Okay, so like as we have already discussed, this is our sample space. Omega is our sample space, and suppose we have a cursive B. Okay, it is a sigma field of subset of omega. Okay, okay. So this ordered pair of the sample space and this sigma field forms a measurable space. This is called, this two tuples is known as measurable space. Okay. Then we define some function, some probability function on this measurable space. On the that is the definition of the axiomatic probability. That will going to be the definition of axiomatic probability actually. Okay. So okay, let this let omega and cursive be a measurable space. Hello, hello. Where do we? Hello. Wait. Okay. Am I audible now? Because there is some network glitch actually.
Yes, sir, you were audible.
Okay, thank you. Okay, so the definition is like defining like omega cursive beta be a measurable space. Okay, and we define a function, a probability function. Suppose P is a probability function from this cursive B to a real line R, real number R. It is said to be, this P function is said to be a probability function if it satisfies the following three conditions. The first condition is like the probability of A is greater than 0 or equal to 0 for all A belong to this cursive B. Okay. The second condition is defined like the probability of the whole space equals 1. Hello. Where do we, would you like to ask something or? Okay, so we have three probability or three axioms actually. Probability of any event A is always greater than or equal to 0. Probability of the whole space equals 1. And the third condition is like if for any sequence of pair was disjoint, if EI belongs to this and EI intersection EJ equal to 5, that is pair void disjoint. Okay, then under this condition, probability of union of EI is equal to summation of probability of EI. Under when these three conditions satisfy, then this P function that is defined from the Borel field RCB to the real line is said to be a probability function. Okay, so we say that thus this omega, the cursive B, and this P is said to be the probability space. Okay, so up to this point, if anyone have any doubt, want to ask anything, then you may ask because there is 1 hour actually past and we need to solve some questions. Is there anyone who have any doubt? No, okay. There are also some properties that I'm just going to read out, like the probability of the empty set is 0, that we already know. Also, finite additivity is also there. Here we see that it is infinite for I from 1 to infinity. Here the union of EI from 1 to infinity. So for at place of infinity, we can put some finite value n as well. So finite additivity property has also be held by the probability function P. The probability function P is a monotone function. A monotone function is implies like if A subset B, then the probability of A is always less than or equal to probability of B. So probability function is a monotonic in nature. Also, the probability of any event E, sorry, any event, the complement of any event A is 1 minus the probability of that event. Okay. So these are some of the consequences of the axiomatic definition of probability. Also, there are some rules. The first one is addition rule is there. We already know these things actually. Probability of the A union B is defined as the probability of event A, probability of event B minus probability of A intersection B. Okay, so this is the addition rule when we have two events. Okay, so when we have three events, when we have n events, there is also a formula. And then there is actually two inequalities there. Like there is a Boole's inequality. Suppose Boole's inequality gives the relationship between the intersection. Like it gives the relationship between intersection. Like if an is a sequence of set in B, suppose a1 is a sequence of set in cursive B, then probability of intersection of AI is always greater than or equal to 1 minus summation of probability of AI complement. So it gives the relationship between the intersection and this. Also, when we have, there is one more inequality, Bonferroni. And this gives the bounds. Okay, this gives the unions are bounded actually. Can anyone confirm? Am I audible?
Yes, sir, you are audible.
Yes, sir, you are
Okay, actually,
audible.
there is. Okay, thank you. Actually, there is a network glitch here. Okay, so Bonferroni inequality. Okay, so it gives the probability of unions are bounded. Okay, so bounds on union. Okay, so like if A1, A2, AN belongs to cursive B, then the probability of union. This probability of union is bounded by the terms. Here it is like summation I from 1 to n probability of the individual AIs minus double summation AI intersection agent. So this probability term is bounded by these two terms. So this gives the, so you may always remember the Bonferroni inequality gives the bounds, okay, of union, and the Boole's inequality gives the relationship between the intersection. Okay. In this, hello.
Yes,
Yes,
sir.
sir.
Okay, sorry. Okay, now we will start to solve some questions on the basis of first week lecture. So if anyone have any doubt or want, okay, is my screen not visible? I think
Sir, it is visible.
it is visible now. Okay, it is visible, no? Okay, so like we have some questions and we will solve those questions step by step. The first one is like in a tuition batch of two students, in a tuition batch of two students, probability that X will pass is 1 by 4 and that Y will pass is 2 by 3. Okay, we need to find the probability that neither of X and Y will pass the exam. Find probability that neither neither of X and Y will pass the exam. Okay, and also we need to assume that the outcomes of X for X and Y are independent. Also assume X and Y are independent. Okay, so there are some options there. I request everyone to like solve this question by their own as well. Okay, I will solve, but I hope you people also try to solve those questions. It's very simple. We are given in a tuition batch of two students. Probability that X will pass is 1 by 4. So the probability like that X will pass is 1 by 4. And also hello,
Yes, sir.
is it visible?
Yes, sir.
Okay. Everyone please try to solve the question as well. Okay. So we are given the X will pass with probability 1 by 4 and Y will pass will probability with probability 2 by 3. We need to find the probability that neither X nor Y will pass. So we need to find that probability X fail and intersection Y fail. Okay, we need to find the probability that X and Y both fail. So first we will calculate probability that X will fail. So X will fail is 1 minus, it's 1 by 4 because the probability of X to be passed is 1 by 4. So fail is 1 minus 1 by 4, which is equal to 3 by 4. Anyone have any doubt? Probability that I will fail is 1 minus 2 by 3, which is equal to 1 by 3. And also we are given these events are independent in nature. We need to find this. So this can be written as like X fail into probability Y fail. Since if A and B are independent, suppose we have two events A and B, and those events are independent events, then probability of A intersection B equals probability of A into probability of B. Okay, and we are here two events. X will fail, neither X will pass nor Y will pass. That means X will fail and Y will fail. So this is equal to X will fail into probability of Y will fail. So probability that X will fail intersection Y will fail is X will fail is 3 by 4 into Y will fail is 1 by 3. So the answer is 1 by 4. Okay. Is it okay up to this point?
Yes, sir.
Okay. These are just simple questions actually. Okay. We have second question. Like suppose we are two dices. Okay. We are given two dices. Two dices are tossed together. What is the probability that the number is either that the product of the number, okay, that the number is either a prime number or divisible by 2. Okay, here actually the product prime, either the product is prime. Either the product of those two number is prime number or is divisible by 2. So let's solve this question. Here we are tossing two dice together. So the sample space is like 1 1, 1 2, and 1 6. Similarly, 2 1, 2 6. Everyone know na, this how the sample space is formed. 6 1, 6 2, 6 6. Okay, so this is the sample space when we roll two dice together. Okay, the first die is either 1 to 6 and the second die has also 1 to 6. So the total number of sample space is 36. Okay, now we are two events actually. The event one is the product is prime. The product is prime. So we can write all those numbers whose product is prime. So the first one is like 1 2, 2 1 is also there. Then 1 3, 3 1 is also there. Then 1 5, 5 1 is also there. Okay. So the number of elements whose product is prime is 6. Okay, up to this point, is it okay? Anyone? Up to this point, is there any problem?
Yes, no, sir.
No. Okay, now the second event is divisible by 2. The product is divisible by 2. So this implies you can see directly that any number which start with 2 1 2, 2 up to 2, 6, then 4, 1, 4, 2 up to 4, 6, and then 6, 1, 6, 2 up to 6, 6. These are a total of 18 numbers actually. First, you can see these are the 6 numbers, these are the next 6 numbers, and these are the next 6 numbers. Also, there are some more numbers like it's 1, 2. Also, the product is divisible by 2. It's 1, 4. It's 1, 6. Similarly, it's 2, 1 is also 2 is completed. So 3, 1. Okay. Okay. So it's 3, 2. It's 3, 4. It's 3, 6. And it's 5, 2. It's 5, 4. It's 5, 6. So the total number of outcomes in the event B is 3, 3, and 3. So the number of elements in B is 18 plus 9, which comes out to be 27. Now the probabilities, we need to find the probability of what is the probability that the number is either product or divisible by 2. Okay. So there is one more thing actually, because event A has these elements, and event B has these elements, 27 elements. But what about okay, sorry, I think the mistakes. What is the probability? Let me check the question once. Two dices are tossed together. What is the probability that the product of the number is either a prime number or the divisible by 2? Okay. Now we need to find the common elements. We need to find A intersection B. So here we can see that this is common. Then 2, 1 is also common. Then there are only two elements is common actually. 1, 2 and 2, 1. So the number of elements in A intersection B is 2. Now the probability. Now we need to find the probability of A union B, which is probability of A plus probability of B minus probability of A intersection B. Okay. So probability of A is the number of elements in A is 6. So the probability is 6 by 36 plus probability of B 27 by 36 minus probability of A intersection B 2 by 36. This comes out to be 36, 6 plus 27 minus 2, which is equal to 31 by 36. This is our answer. Okay. Anyone have any doubt that how we have calculated the probability? Anyone? Okay, then we will solve the next question. There are 7 apples. Okay, so there are 7 apples, 5 mangoes, and 10 guavas in a basket. Okay. 4 fruits are selected at random, one by one, without replacement. Selected at random, one by one without replacement. Without replace. These are the simple one actually. We need to find the probability that the first fruit drawn is a mango. The first fruit drawn is a mango. The second is guava. Third is an apple. And the fourth one is again a mango. So we need to find the probability that we draw four fruits from a basket having seven apples, five mangoes, and 10 guavas. Then we need to find the probability that the first one is mango, the second one is guava, the third one is an apple, and the fourth one is again a mango. So the required probability is like the first one is mango. Suppose PM is stand for probability of getting mango in the first trial. So we have a total of 7 plus 5 plus 10. So it's 7, 5, and 10. It's 22. Total of 22. And out of those 22, we have 5 mangoes. So the probability of drawing a mango in the first trial is 5 by 22. Then we need to draw guava, the guava in the second attempt. So now there is a total of 21 fruits in the basket because we hello.
Yes, sir.
Thank you.
Now you are
Uh,
audible again,
so
sir.
okay, thank you. See here, we perform this experiment without replacement. Actually, my screen is not visible. I think.
It is bit slow loading.
Sir, it's visible.
Okay, wait. Visible. It's visible, but I have already written something, but not.
Yeah, whatever you are writing, there is a delay, sir.
Okay, now it is visible. I think. Yes. Thank you.
Yes.
So here again, let me read the question. So we have a basket having seven apple, five mangoes, and 10 guavas. Okay. And we need to draw four fruits one by one without replacement. Okay. So the first fruit is mango. The probability of drawing a mango from the basket having 22 total fruits, and out of those 22, five are mango. The probability of mango is 5 by 22, as simple. Okay. Now, in the second drawing, we need to draw the guava. So, the probability of getting guava in the second draw is now there is 21 fruit in the basket. So, the probability is the total number of fruit is 21, and the probability of guava is like the favorable number of guavas is 10. So, 10 by 25. It's 10 by 21. Now, the third one is we need to draw an apple. An apple is drawn. Now, there are a total 20 fruits in our basket. And out of those 20, we have 7 apples. So, 7 by 20. And at last, we again need to draw mango in the fourth draw. So, in the fourth draw, there is a total of 19 uh, fruits in the basket, and out of those, in initial there are five mangoes, but now one is drawn at the first trial, so there is four. Okay, so collectively using the multiplicative rule, the required probability is it's PM. Let me write directly. It's 5 by 22 multiplied by 10 by 21, multiplied by 7 by 20, multiplied by 4 by 19. This is the required probability of getting two mango, one guava, and one apple. Then we perform without replacement is, and after solving, it will comes out to be 5 upon 627. That means very less probability, less than 1%. Okay. So the next question is, please everyone, if you have any doubt, you may directly ask me. Okay. These are the simple questions actually. The next question is, one ball is drawn at random. One ball is drawn at random from each of two baskets. Each of two baskets. Okay. Hello.
Yes, sir.
Yes, thank you. Where first basket contains 3 red and 5 black balls, and second basket has 4 red and 7 black balls. Okay. The question is, one ball is drawn at random from each of the two baskets. Okay. And where the first basket contains 3 red and 5 black balls, and the second basket has 4 red and 7 black balls, then we need to find the probability that both the balls are black. Probability that both balls are black. We need to find this. Okay. So everyone, please try to solve this question. Again, the question is like, suppose we have two baskets. In the first basket, we have the number of red ball is 3 and number of black ball is 5. In the second basket, we have a number of red ball is 4 and number of black ball is 7. And from each basket, we need to draw one ball. So we need to find the black ball. So probability of black ball when basket 1 is, that's only notation given. It is not the conditional probability. Okay. The black ball when we choose basket 1 is 5 by 8. Similarly, probability that black balls when we choose the second basket is 7 by 11. So the probability that both the ball will black is, the required probability is 5 by 8 into 7 by 11, because these two are also independent. So this comes out to be 5s are 35 and it's 38. So this is our required probability. Okay.
Sir, I have a
Now,
doubt.
yes, you may ask.
Sir, if we are choosing basket 1 and basket 2, so won't be multiplied by 1 by 2, and why are we not multiplying?
Okay, the question here says one ball is drawn at random from each of the two baskets. Okay, so you have two baskets. First, you need to draw one ball from basket 1 and then from one ball in basket 2. What you are telling is we will going to discuss in the conditional probability section. When we choose basket 1, although if we need to, like here 1 by 2 is not going to multiply because we need to draw one ball from each basket. Suppose we need to draw one ball from one basket randomly and then choose the second time one random basket, then it may possible the first basket and then the second basket will be there. Okay. But wherever I can think, whatever like I can think, those topic is included in the conditional probability that we will discuss in the second week course.
Okay, sir. Thank you.
Okay. Anyone else? Okay, then the next question is, suppose a die is rolled twice. This is a good question actually. A die is rolled twice independently. Okay, what is the probability that the first throw shows a number less than or equal to 3? Add or equal to 3 or the second throw shows at least 5. Okay, so we have a question. Die is rolled twice independently. What is the probability that the first throw shows a number less than or equal to 3, or this or is stand for union? Okay, always remember when we have or, this implies union, and when we have and, this implies intersection. Okay. So we need to find that the first throw, the number is either less than or equal to 3, and or the second throw shows at least 5. Okay. So just visualize all those 36 pairs. Okay. 1, 1, 1, 2, 1, 6 up to 2, 2, 2, 1, 2, 2, 2, 6, 2, 6, 1, 6, 2, 6, 6. There are 36 pairs. Okay. And from those 36 pairs, we need to find like those events. Like event A is number less than or equal to 3. Okay. So out of those 36 events, just visualize how many events will be there in this set A. So obviously less than 3, the first row. So we need to focus on first row. It's 1, 1, it's 1, 2, it's 1, 3, 1, 4, 1, 5, and 1, 6. Similarly, it's 2, 1, 2, 6. Similarly, it's 3, 1, 3, 6. Up to this point, anyone have any doubt? Like here, we have total of 6. Okay. Again, the 6. Again, the 6. Because event A is defined as numbers less than or equal to 3 in the first row. In the first row. Okay. Let me write here as well. So event A contains a total of 18 elements. Okay. Now event B is defined as at least 5. at least 5 in second throw. So obviously event B is like at least 5 in second, so it's 1 5 1 6. It's 2 5 2 6. Similarly, it's 6 5 6 6. Okay, so again, just try to visualize the 2 for 1, the 2 for 2, the 2 for 6. So the 2 for 5, the 2 for 4, and the 2 for 3. So number of elements in B is, here number of element in A is 18 and number of elements in set B is 2 into 6, comes out to be 12. Okay, now we need to calculate OR, that is union. So we need to find the probability that A union B, which is probability of A plus probability of B minus probability of A intersection B. So the next step is to find the elements in A intersection. So A intersection B contains, like here, it's 1 1 1 2 1 3. So it's 1 5 and 1 6 is there, 2 5 and 2 6 is there, and 3 5 and 3 6 is there. Okay, so it's 1 5 1 6 2 5 2 6 3 5 3 6. So the number of elements in A intersection B comes out to be 6. Now we can calculate the probability of A union B equal to probability of A. Probability of A is 18 divided by 36. 18 divided by 36 plus, sorry, right here. It's 18 divided by 36 plus probability of B is like 12. So it's 12 divided by 36 and minus 6 divided by 36. In the simple calculation, 36, 18 plus 12 minus 6 is 24 upon 36. So it comes out to be probability of A union B equal to 2 by 3. So that means the first one is either at least 3 and the second one is at most, sorry, telling wrong. The first one is at least 3, at least less than or equal to 3, and the second one is at least 5. Okay, so this is the probability of getting, it's 2 by 3. Is it okay up to this point?
Can you please repeat this question once again?
Sorry. Okay, got it. Let me repeat the again question. Here, we are given the question is like a die is rolled twice independently. What is the probability that the first throw shows a number less than or equal to 3, and or not and sorry or the second throw shows at least 5? Okay, so just first visualize the 36 ordered pair, okay, which comes in the sample space: 1 1 1 2 1 3 up to 1 6. Similarly 2 1 2 2 up to 2 6 and 6 1 6 2 up to 6 6. So there is a 6 cross 6 kind of matrix is there. Okay, so it contains 36 elements. Now the event A is defined as like in first throw a number less than or equal to 3 occurs. So we write those set in roster form as here. So first one is like 1 1 1 2 1 6. So first element must be less than or equal to 3. So 1 1 1 2 1 6, 2 1 2 2 up to 2 6, and 3 1 3 2 up to 3 6. Because as when we write 4 1, it like disobeyed the first rule. Okay, the less than or equal to 3. So that means a total number of element in set A is, sorry, in event A is 80. Okay. Again, the second condition is given the second row shows at least 5. So at least either 5 or more than 5. So we have only two options, either 5 or 6. So the event B contains 1516, 2526, 3536, then 4546, 5556, and 6566. So there is a total of 12 elements in set B. Okay, so now we need to find the probability that or number less than or equal to 3 or at least 5. So union is there. And when there is union, we need to find the probability A union B, and which is defined as probability of A plus probability of B minus probability of A intersection B. So our next step is to find out the number of elements in set A intersection B. So A intersection B contains, since we have already written here, event A and event B, from there you can directly write what comes out to be in A intersection B, which is 1516, 2526, and 3536. So there is a total 6 element in intersection. Now using the additive rule of probability of A union B equal to A plus B minus A intersection B, and just simple calculation, and we will find 2 by 3. Is it okay?
Yes, sir. Thank you, sir.
Okay. Okay, now similarly, we have one more question. Suppose we have a deck of card. Okay, everyone know the distribution of cards, no? Or is there anyone who do not know the distribution of card? Everyone know? Okay, then the question is, from a pack of 52 cards, two cards are drawn together at random. Two cards are drawn together at random. Then what is the probability of both the card being king? So probability that both card king. Okay, so if there is any doubt regarding the distribution, then please ask. Otherwise, you are not able to understand this question. So we need to find the probability of getting two cards drawn simultaneously, be king. So there is total 4 cards of king. Okay, there are 4 kings in a deck of 52 cards. Okay, so out of those 4 cards, we need to draw 2 cards from those 52 deck of cards. Okay, so in favor, how many elements are there? So there is a total of 4 kings in a card, in a deck. And out of those 4, we need to draw 2. So there is a total 4C2 options available to draw those 4 cards, for those 2 kings from those 4 kings. And we have a total of 52 cards in a deck. And out of those, there is a 50C2, 52C2 options are there to draw any 2 cards from a deck of 52 cards. Okay, so the number of favorable cards is 4C2 and total cases as 52C2. And if anyone do not know NCR, the combination is there actually. So NCR is n factorial, r factorial, n minus r factorial. This is the formula. So obviously it comes out to be 4 into 3 into 2 factorial. 2 factorial, it's 4 minus 2 factorial, and whole divided by 52 into 51 into 50 factorial. It's 2 factorial. It's 52 minus 2 factorial. And just a simple calculation, if you are able to solve this, it's 4 into 3. See, this 2 factorial will be cancelled out with this, And this 4 minus 2 is again 2 factorial, and the value of 2 factorial is actually 2. So it's let me write here by 2, and whole divided by 52 into 51. This cancel by this and divided by this. Now after solving this, we will get 1 upon 221. If anyone have any problem how to solve this, I can solve this here as well. Okay, it's simple. It's 4 cross 3 by 2 into 2 upon 52 cross 51. It cancels out to be cancel out. And then 4 and 3. So it cancels out to be 17. It's cancel out to be 30. So it comes out to be 1 upon 13 into 17. And then it's 1 upon 13, sorry, 221. So this is our required probability of getting 2 kings simultaneously from a deck of 52 cards. Okay, is there any doubt in this question? Anyone? Okay, now the next question. The next question is, let E1, E2, E3 be 3 independent events. We have E1, E2, E3 be 3 independent events. Such that the probability of EI equal to 1 minus 1 by 2 to the power I, where I is running from 1, 2, and 3 only. Then we need to find the probability that exactly 2 of the event occur. So find probability that exactly 2 of the events occur. We need to find the probability that exactly 2 of the event occur. Is it feasible? Okay. So we need to find the probability that exactly 2 of the 3 event occur. Okay. So first we need to find the probability. So like probability of E1 is 1 by 1 minus 1 by 2, which equal to 1 by 2. Probability of E2 equal to 1 minus 1 by 2 to the power 2, that is 1 minus 1 by 4, which is equal to 3 by 4. And probability of E3, which is equal to 1 minus 1 by 2 to the power 3, which is 1 minus 1 by 8, which comes out to be 7 by 8. Okay, so these are the probability that E1, E2, and E3 occur respectively. Okay, now we need to find the probability that exactly 2 of the event occur. Okay, so the chances is like if E1 occur, E2 occur, then E3, a complement of E3, that is ET does not occur. Okay, then if E1 occur, suppose E1 does not occur, then E2 occur and E3 occurs. And at last, then E1 occurs, E2 does not occur, and E3 occurs. These are the 3 possible scenarios when exactly 2 of the 3 event has occurred. Okay, so we need to find the probability of E1, E2, E3, which we have already calculated here. Now, E1, E2, and E3 complement should also be known. So we can write here directly. So probability of E1 complement 1 minus probability of E1. So it comes out to be it's 1 by 2. So 1 minus 1 by 2 again 1 by 2. probability of E2 complement 1 minus probability of E2, which is equal to 1 minus probability of E2 is 3 by 4, which is 1 by 4, and probability of E3 complement equal to 1 minus probability of E3, which is equal to 1 minus 7 by 8. The probability of E3 is 7 by 8, which is 1 by 8. So now we need to find this probability. Okay, these are the wrong notation, just I am writing. So probability is like probability of E1, E2, E3 complement plus probability of E1, E2 complement E3 plus probability of E1 complement E2, E3. And it is given in the question that E1, E2, and E3 are independent events. So that means this can be written as probability of E1 into probability of 2 into probability of E3 complement. Similarly, this can be written, and similarly, this can be written. Okay. So the intersection term can be written as a product of their individual probability. Now we need to write this. So it's 1 by 2 into 3 by 4 into it's 1 by 8 plus 1 by 2 into 1 by 4 into 7 by 8 plus it's 1 by 2 into it's 3 by 4 into it's 7 by 8. So just a simple calculation again. We need to solve this, and after solving, we will find out it's 31 divided by 64. So this is the required probability that exactly 2 of the 3 events has occurred. It's 31 by 64. Okay. We have some more questions like this question is somewhat interesting. Suppose we are given two independent event E and F are such that we are given E and F are independent event. Also, we are given the probability of E intersection F equal to 1 by 6. Probability of E complement intersection F complement equal to 1 by 3. And probability of E minus probability of F is greater than 0. This implies probability of E is more as compared to probability of F. Okay, probability of E is greater, probability of F. We need to find probability of F complement. Okay, so again, just simple question, just some calculation is there. Like we are given independent event. Okay, so that means probability of E intersection F can be written as probability of E into probability of F, which is also given 1 by 6. Okay, for simplicity purpose, let's take probability of E equal to A and probability of F equal to B. For simplicity purpose only. Okay, so that means what? A into B equal to 1 by 6. Or we can write A equal to 1 by 6B. Okay, this is one equation. The second equation is E complement intersection F complement. So probability of E complement intersection of complement F complement equal to 1 by 3, which is equal to probability of E complement into probability of F complement. Now the probability of E equal to A. The probability of E complement is 1 minus A, and probability of F complement is 1 minus B. We need to just solve this, multiply this. So it's 1 by 3 equal to 1 minus b minus a plus ab. Okay, you can directly put the value of ab equal to 1 by 6 here, even if you want. Okay, and then solve this question. So after solving this, we have one equation like put a equal to 1 by 6b in this, we get 6b square minus 5b plus 1 equal to 0. So this equation is constructed with the help of the substitution of a equal to 1 by 6b. Now we need to solve this question. Just a simple quadratic equation. It's 6b square minus 3b minus 2b plus 1 equal to 0. We can take 3b as common. It's 2 minus 1. 2b minus 1. Minus 1 is taken. It's 2b minus 1 equal to 0. So it's either 2b minus 1 or 3b minus 1 equal to 0. So from here, it's b equal to either 1 by 2 or either 1 by 3. Okay. And b is the probability of f. So a equal to either 1 by 3 or 1 by 2. We are also given like here, probability of E minus probability F is greater than 0. Since probability of E minus probability of F is greater than 0, so this implies obviously probability of E equal to 1 by 2 and probability of F equal to 1 by 3. Now we need to find the probability that F complement. The question says find the probability that F complement. Okay, so it's 1 minus probability of F, which is equal to 2 by 3. The final answer. Is it okay up to this point? Anyone?
Yes, sir.
Okay, thank you. Okay, there is one more question, probably the last one. Suppose we have a box contain 1,000 light bulbs. Okay, a box contains 1,000 light bulbs. The probability that there is at least one defective bulb in the box is 0.1. So I'm not going to write the question, I'm just write the symbol. Okay. So the probability that suppose, let me first write X the number of defective bulbs. Okay. And suppose the total number of bulbs is 1,000 is there. Okay. So we are given the probability that there is at least one defective bulb. So defective bulb is X, and at least one defective bulb, that is X is greater than or equal to 1. That is at least one, either one or more than one. X is contains the value either 1 or more than 1, that is 2, 3, 4 up to 10, 1,000. So probability that X is greater than or equal to 1 is 0.10. Also, we are given the probability that there are at least two defective bulbs. We are also given the probability that at least two or more than two, that is 2, 3, 4, and so on up to 10, 1,000. So probability that X is greater than or equal to 2 is 0.05. We need to find the probability that the box contain at most one defective. Find the probability that box contain at most one defective bulb. Just try to understand what the question is first. Okay, we are given the probability that at least one defective bulb is 0.1. The probability that at least two defective bulb is 0.05. We need to find the probability that the box contains at most one defective bulb. At most one defective bulb. So that means either one or less than one. So we need to find the probability that X is either 1 or less than 1. So either 0 or 1. Simple. Okay. Now for the visualization purpose only, it's 1, 0 is 2. So greater than 2 is this quantity, and greater than 1 is this quantity. So that means we have you can write like this if you want. So probability that X is less than or equal to 1. This is X is less than 1 plus probability that X equal to 1. Up to this point, is it okay? Up to this point, is it okay? We need to find the probability that the box contains at most one defective bulb. Okay, so at most one defective bulb implies either 1 or 0. So either X equal to 0, we can write X is less than 1 because number of bulb is countable, either 1 or 2 or 3. Okay, so X is less than 1 plus X equal to 1. Now we need to find the probability that 1 and 0. Okay, so from the first condition, this probability that X is greater than or equal to 1 equal to 0.1. So this implies probability that X is less than 1 equal to 1 minus 0.1, which comes out to be 0.90 with the help of the complementation property. Okay. Now, again, probability that X equal to 1. This can be, okay, how can we find this? With the help of this figure. Here, 2 greater than 2 and greater than 1. Sorry, greater than or equal to 2 and greater than or equal to 1. The difference is the 1 at probability at 1 as well. Okay, so this can be the probability that X is greater than or equal to 2 minus probability that X is greater than or equal to 1. The difference between this is probability that X equal to 1. So this implies 0.95 minus 0.90, that is 0.05. So we need to find the probability that X is less than or equal to 1, which is equal to probability of X is less than 1 plus probability that X equal to 1 is 0.90 plus 0.05 comes out to be 0.95. Is there any doubt in this question? Anyone? Any doubt? Okay, thank you. Is there any question you people? Okay, problem. So these are the questions. Okay, if anyone have any doubt up to this point, you may ask. Otherwise, we can maybe conclude our session here. Is there any doubt, any question, or anything you want to share? Anyone? Okay, then let's hope that we conclude our session here now. Okay, so let me first stop the recording.